Recall back when we learned that the absolute value of a number is simply its distance from 0. We're going to apply this idea to equations now. We know that the absolute value of 4 and the absolute value of -4 are equal because both values are the same distance from 0. But what if we have the absolute value of x, where x is any real number? Let's assume we have the absolute value of x equals 4. What's being asked is, since the absolute value of x is 4, how far is this value from 0? We would then say that the solutions of the absolute value of 4 is x equals 4 and x equals -4. But what happens when we have an entire expression inside of the absolute value? The objective remains the same. Let's call our expression e. E can stand for any expression we desire, such as 2x plus 3. If we are given the absolute value of 2x plus 3 equals 5, we're being asked what values of x makes 2x plus 3 equal to 5. We will use the same idea as looking for the absolute value of x equals 4. We're going to solve for both 5 and -5. Let's work through both options. Option 1 has 2x plus 3 equals 5. Solving for x, we get x equals 1. Option 2 has us solving 2x plus 3 equals -5. Solving for x again, we get x equals -4. This should be familiar to you by now as we're solving for x. In the last lesson, solving for x gave us a specific answer in our linear equation. Here, solving for x gave us two solutions. But what do these two solutions mean? We won't cover graphs until next unit, but let's get a sneak peek. Looking at the graph of the absolute value of 2x plus 3, if we follow the x-axis to both x equals 1 and x equals -4, we'll notice that the corresponding y values are both 5. This means that either value, x equals 1 or x equals -4, will produce the true result of the absolute value of 2x plus 3 equals 5. Let's look at a property worth memorizing for absolute value equations. The property of absolute value equations. For any variable expression e and any non-negative real number n, the absolute value of e equals n if and only if e equals n or e equals -n. Let's look at what this property is talking about. I use the letters e and n for two reasons. First, more importantly, n is our distance. It's also required to be non-negative. That's because if we think about distance physically, the smallest distance is 0. We cannot have a negative distance. Now the letter e doesn't represent any single number or variable, even though it can. I used e to represent expression. We can have an entire expression inside our absolute value bars. This property is telling us that the absolute value of an expression is true, such as when we have the absolute value of 2x plus 3 equals 5, if and only if e equals n is true, such as 2x plus 3 equals 5, which we found to be x equals 1, or e equals -n is true, such as 2x plus 3 equals -5, which we found to be x equals -4. Let's see how this works with a few examples. Number 1. The absolute value of x plus 3 equals 6. Remember our property for absolute value equations. It says that the absolute value of an expression is equal to a number n if and only if that expression equals n or -n. In other words, we need to solve for x plus 3 equals 6 and x plus 3 equals negative 6. Solving x for both equations gives x equals 3 and x equals negative 9. That means both x equals 3 and x equals negative 9 are both solutions to our absolute value equation. Let's plug them both in and see. For the first one, the absolute value of 3 plus 3 equals the absolute value of 6 equals 6. Then the second one, the absolute value of negative 9 plus 3 equals the absolute value of negative 6 equals 6. Both solutions gave our original number, n equals 6. That's showing that we have the correct solutions. Number 2. Here we have another simple equation, but with the difference instead of a sum. The same rules apply. We're going to solve 3x minus 4 equals 1 and 3x minus 4 equals negative 1. The first equation gives x equals 5 over 3. And the second equation gives x equals 1 as our solutions. Now let's check them. The absolute value of 3 times 5 over 3 minus 4 equals the absolute value of 5 minus 4, which equals the absolute value of 1, which equals 1. And the absolute value of 3 times 1 minus 4, which equals the absolute value of negative 1, which equals 1. Since we get the same answer, we know we have the right solutions. Number 3. The absolute value of 2x minus 1 equals negative 2. Recall that our number n must be a non-negative number. That means this equation will produce no solutions. But just to illustrate, let's try anyway. We need to solve both 2x minus 1 equals negative 2 and 2x minus 1 equals 2. The first equation gives x equals negative 1/2. And the second equation gives x equals 3/2. Let's plug these two solutions into our absolute value equation. The first one gives the absolute value of 2 times negative 1/2 minus 1 equals the absolute value of negative 1 minus 1, which equals the absolute value of negative 2, which equals 2. And the second one gives the absolute value of 2 times 3 over 2 minus 1, which equals the absolute value of 3 minus 1, which equals the absolute value of 2, which equals 2. Notice that both solutions gave us a positive 2 rather than a negative 2. That's because absolute values give distances from 0, and a negative number cannot be an actual distance. We can see visually why this is so. Looking at the graph of the absolute value of 2x minus 1, notice that the entirety of the graph is above the x-axis. Number 4, the absolute value of x plus 1 divided by 3 equals 4. Let's raise the difficulty slightly. We're going to solve an absolute value equation involving a rational expression. Once again, our same rules apply here. Nothing changes. Let's get our two solutions. First, x plus 1 over 3 equals 4 implies x plus 1 equals 12, thus x equals 11. And second, x plus 1 over 3 equals negative 4 implies x plus 1 equals negative 12, which gives us x equals negative 13. So you have x equals 11 and x equals negative 13. Let's plug these two solutions and check if they're accurate. The first gives the absolute value of 11 plus 1 over 3, which equals the absolute value of 12 over 3, which equals the absolute value of 4, which equals 4. And the second solution gives the absolute value of negative 13 plus 1 divided by 3, which equals the absolute value of negative 12 divided by 3, which equals the absolute value of negative 4, which equals 4. Both of those solutions gave us a 4, which confirms the accuracy of our solutions. Number 5. 2 times the absolute value of x minus 7 minus 6 equals 0. Sometimes you'll see multipliers outside of our absolute value expression. In this expression, we have a 2 that we can divide out with the rest of the equation that we can then simplify to give us the absolute value of x minus 7 equals 3. Now we can find our solutions. Solving for 3 and negative 3, we get x minus 7 equals 3, which implies x equals 10, and x minus 7 equals negative 3, which implies x equals 4. We'll now check these solutions. 2 times the absolute value of 10 minus 7 minus 6 equals 2 times the absolute value of 3 minus 6, which equals 6 minus 6 equals 0. And 2 times the absolute value of 4 minus 7 minus 6 equals 2 times the absolute value of negative 3 minus 6 equals 6 minus 6, which equals 0. Notice that I used the original expression before we simplified. It doesn't matter which one you use. For example, for x equals 10, the absolute value of 10 minus 7 equals the absolute value of 3, which equals 3. We still get the correct answer, so our solutions are correct. Number 6, the absolute value of x plus 5 equals x plus 5. One final example. This is a slightly different question compared to what we've been working with. Notice that we essentially have the absolute value of e equals e. We are not being asked what's the absolute value of itself. We are being asked when is the absolute value equal to itself? Or what value or values of x makes x plus 5 equal to x plus 5? Because of this, we need to take a look at the fundamental definition of the absolute value. Recall that the absolute value of n is equal to n if n is greater than or equal to 0, and negative n if n is less than 0. Our example matches the first case. So we have x plus 5 is greater than or equal to 0. Solving this inequality gives us x is greater than or equal to negative 5. More formally, something like this can be written in set notation. The set of all x such that x is greater than or equal to negative 5. In interval notation, you would write negative 5, infinity. We can see this visually when looking at both graphs. I have the blue graph on top. That is x plus 5. The red graph, which the right side is underneath the blue side, is the absolute value of x plus 5. Notice that when we get to x equals negative 5, and then above, both the graphs overlap. Thus, the absolute value of x plus 5 equals x plus 5 only when x is greater than or equal to negative 5. Absolute value equations are highly useful in different branches of mathematics. You find them a lot in physics when dealing with distances of different types, for example. Absolute values can be annoying to deal with at first, but if we take our time with them and don't forget the fundamental definitions, we'll do just fine. This is the end of Chapter 1. Some instructors prefer to move directly to graphing after introducing equations. I think I will hold off on graphing until we introduce functions, since they are analytically connected. Instead, for Chapter 2, we're going to move on to quadratic equations.